atmospheres, correct?
If you didn't cancel out R, yes. And even if you do cancel out R, you would have to use Kelvin. You can never not use Kelvin, whether or not R is there.
Okay, so is it better if I always just convert it to Kelvin and atmospheres just to make sure?
If you're nervous about it, sure.
Okay.
Yes.
Thank you.
Okay, so let's go on. If there are no more questions about this particular problem, the next one that you asked about was number 60. So finding number 60 on your pages. Let me just erase this problem here. And you're reading over number 60 while I erase. Okay. So number 60 reads, an ideal gas at 7 degrees Celsius is placed in a spherical flexible container having a radius of 1 centimeter. The gas is heated at constant pressure to 88 degrees Celsius. Determine the radius of the spherical container after the gas is heated. All right, so we have a sample of gas in a spherical container. Think a ball. And our gas is in this little ball. And again, the gas is unnamed. We've got our sample of gas in here. Okay, what information do we have right now about this gas other than it's in a flexible spherical container? What numeric information do we have? Anybody for number 60? I'm just going to shut the door while you look up that information. Okay, that's better. So, what do we know about this gas? Anyone? Number 60, what do we know about this gas in the spherical container?
Its temperature.
Its temperature. What temperature is it at?
78 Celsius.
Well, no, it's not 78. It's
7.
7. It's 7 degrees Celsius.
Oh, whoops.
Okay, do we ever like Celsius?
No.
Never, ever, ever like Celsius. So you're converting this. So if we convert this plus 273.15, this is 280.15 Kelvin. Any other information we have about this gas? And the information I'm looking for is in the very first sentence. Something else that I could write down about this gas that I get from the first sentence of the problem.
It's a flexible container.
Okay, we know it's flexible, but I'm looking for some numerical information.
The radius.
The radius of this flexible container. So let's note that the radius is this distance here. This is the radius, R. And what is the radius anyway? What is the radius in this case? It's 1.
1 meter.
1 centimeter is the radius. Why do you think we were supplied with the radius? What could the radius allow us to calculate? What is
volume.
the volume? Exactly. All right, you've got the measurement of radius for a sphere. We could calculate the volume of this container. So the formula to get volume is 4/3 pi r cubed. So substituting in that 1, 4/3 pi times 1 centimeter cubed is going to give you the volume of this spherical container. So radius and volume are closely related. So hopefully you guys are working this out. I get 4.188, let's call it 8. 4.1888, and the units are cubic centimeters. I haven't moved on from the first sentence yet. This is just the first sentence of the problem. So now I'm going to move on to the second sentence. The gas is heated at constant pressure. Okay, so we're heating it. And what happens to a gas in a flexible container when you heat it? What change can you expect to happen? This is key. We got to know what change to expect.
It expands.
It's going to expand. All right, you heat a gas, it expands. That's the automatic thing we should think of. All right, in other words, our flexible container gets bigger. Oh, it's a terrible diagram. Let's try and do that again. There we go. Slightly better here. So here's our container now. Did we add any extra gas to the container? Does the problem say we added gas? Well, it doesn't say that. All right, we didn't add any gas. We didn't remove any gas. All right, all we did was heat it up. We heated it up. Everything else is staying constant. Okay, what do we now know about the gas after we've done the heating? We've done the heating. What do we know now from the problem? What does it say we know now?
Temperature.
We know the temperature. Okay, so we heated it up. And we know the new temperature. The new temperature is 88 degrees Celsius, or if we're working it out in Kelvin, I can't do that in my head, not at 10 in the morning before the tea has kicked in. Here we go. So we have the temperature after we've heated it. What's the goal of the problem, though? What do we actually want to obtain?
Radius.
The radius. Do you think the radius is going to be larger or smaller than 1?
Larger.
Larger. All right, we expect a bigger radius. Why? Because what happened to the container? What was the magic word? The container did what?
Expanded.
Expanded. All right, expanded. So we expect the radius to be bigger because the container expanded. Now, do we have a gas law that involves temperature and radius? Of all the gas laws you've studied, is there a gas law with temperature and radius in it?
Charles' law.
Nope, Charles' law doesn't have radius in it. What does Charles' law have in it?
Oops.
Temperature and radius. Is there a law with temperature and radius?
Ideal gas law.
All right, nope, there's no radius in temperature. Our ideal gas law, PV equals nRT. I don't see radius in that law. Charles' law, V1 over T1 equals V2 over T2. I don't see radius in that law. The answer is no. All right, there is no gas law that you have met that looks at the relationship between temperature and radius. So even though our goal is to figure out the radius here, we don't have a direct relationship between temperature and radius. So we need to use a different relationship to help us. We need the relationship between what and what to help us.
Would be temperature and volume.
You got it. Okay, so the fundamental relationship we're going to look at is temperature and volume. All right, we know the initial temperature and the initial volume. We have the new temperature over here, which means we could solve for the new volume. Now, why would I want to solve for the new volume? How would that help me get the radius? Well, let's think about things one at a time. Let's first work out what the new volume is. If I'm going to work out the new volume, which is going to be bigger than the old volume, we're going to have to use Charles' law. All right, V1 over T1 equals V2 over T2. We have everything except V2, and so we have to plug and chug and solve for V2. So V2 is going to be our new temperature, 361.15, times our original volume, 4.1888, divided by the original temperature, 280.15. And I get a new volume of 5.3999 cubic centimeters when I plugged and chugged. But we're not interested in the new volume. The goal of this problem is to get the radius, the new radius. So how are we going to get the new radius? Well, we know that volume and radius are connected. How are volume and radius connected? What's the equation that connects volume and radius? I already wrote it down. It's already written on this page. What's the equation that connects volume and radius? It's volume equals 4/3 pi r cubed. Except this time the volume has changed. This is the volume now. So now we know the new volume. We can solve for the only variable, which is the new radius. And if you plug and chug and solve for the new radius, all right, it should be bigger than the original radius. The original radius was 1 centimeters. We know that the spherical container expanded, so we should get a radius that is greater than 1. So in this case, if I just work this out, times 3 divided by 4, divide by pi, take the cube root, I end up getting a value of 1.09 centimeters as the value for R.
I have a quick question.
Mhm.
I did it a couple times. I keep getting 5.4005 for the volume of V2.
5.4005.
Yeah.
Okay, so V2 is going to be equal to V1 times T2 over T1, or V1, which is 4.1888 times T2. And I don't know if you have the right numbers. These are the numbers that you're using?
4.1888 times 361 divided by 280.
All right, so I'm using the full, all right, 280.15 and
Oh.
361.15. So that's why we might have a slight difference, but let me double check. Times 361.15 divided by 280.15, and I'm still getting the same answer. So it could be that by not using the 0.15, you're just slightly off.
Okay.
So yes, in this problem here, we had to realize that the fundamental change taking place was a change in the volume of the system. The change in the volume. We heat it, gases expand, volume increases. And so the relationship that was going to help us out here was ultimately Charles' law. Now, once again, there was a way to do this a lot faster than all of this plugging and chugging. And so again, I want to show you the way to do this quickly. And of course, to do it quickly is going to involve some substitutions. Okay. Okay, so let's call this R over here R1. That's the original radius of the sphere. And let's call the radius that we're trying to get R2 after the expansion has taken place. Now, ultimately, we know that volume is changing, that the volume here, V1, is not going to be the same as the volume here, V2. All right, and that's because expansion is taking place. Expansion is taking place. We also know that when gases expand because of a temperature change, that we're still dealing with good old Charles' law, V1 over T1 equals V2 over T2. Okay, well, we also know that because it's a spherical container, that the volume of a spherical container of a gas is equal to 4/3 pi r cubed. And so once again, we can make a substitution. Instead of writing V1, I could therefore write 4/3 pi r cubed over T1. Except the R that I would have here would be R1. And on the other side of the equation, instead of writing V2, I could write 4/3 pi r cubed over T2, except the R this time is R2. So all I did was substitute 4/3 pi r cubed for V1 and V2, making sure that the R's were R1 and R2. And of course, this equation can be simplified. We can get rid of the pi on both sides. We can also get rid of the 4/3 on both sides, which means in the end, all right, we have a streamlined equation, which is simply R1 cubed over T1 equals R2 cubed over T2. And now it becomes just a one-step problem because we know R1, we know T1, we know T2. We just have to solve for R2. In other words, we didn't actually have to solve for volume at all if we were clever about how we approach the problem. Okay, any questions about this? To remember also, I cannot read any chat comments at this time. I'm unable to read the chats when I'm in the whiteboard mode. Okay, I'm not seeing any frantic hands waving, so I'm going to move on. So that was number 60. The next question I'm asked for is number 71. 71. So let's just clear this all. So going through the list here. So number 71 says a 15-liter rigid container, rigid is important, all right, was charged with 0.5 atmospheres of krypton gas and 1.5 atmospheres of chlorine gas at 350 degrees Celsius. The krypton and chlorine react to form krypton tetrachloride. What mass of krypton tetrachloride can be produced, assuming 100% yield? So imagine, if you will, that you have a rigid container. If the container is rigid, what does not change? What does not change for a rigid container? What stays the same if the container is rigid? This is key. We can't do the problem if we don't understand what we're being told, if we're told the container is rigid.
The volume.
The volume stays the same. So when we're told that the volume is 15 liters, it's always going to be 15 liters. It's always going to stay as 15 liters. So we are putting some gases into this container. What gases are being placed in this container? Krypton gas is being placed in this container, and chlorine gas is being placed in this container. Okay? And what we're given are the pressures, the partial pressures of each of these two gases. We're told that the pressure exerted by the krypton gas is equal to 0.5 atmospheres, and that the pressure exerted by the chlorine gas is 1.5 atmospheres. Let me double check that. 1.5 chlorine and 0.5 for the krypton. We're also told, all right, that the temperature is 350 degrees Celsius, which you're going to convert to Kelvin right away for me, because we never use Celsius under any circumstances. So that's 623.15. Okay, so here's the information that we start with. All right, we have the krypton, we have the chlorine. Okay, well, what happens? It says that the krypton and chlorine react. So there's a reaction that takes place between the krypton and the chlorine. And what is that reaction? It says they react to form krypton tetrachloride. So we're going to have to write an equation for this reaction. So krypton gas plus chlorine gas are going to react and form krypton tetrachloride, KrCl4 gas, which means we just need to balance this with a 2 here. 2 here, a 1 here, and a 1 here. Okay. And we are now asked what mass of krypton tetrachloride can be produced. So our goal is to get the mass of the gas. Okay, so what kind of problem is this ultimately? If we're trying to figure out the mass of the product, this is a stoichiometry problem. So we need to recognize that this is a stoichiometry problem. And as always, we can do it the long way or we can do it the short way. Let's start by doing it in the long way. So first we have to recognize that this is a stoichiometry problem. Okay? In a stoichiometry problem, all right, the first step is always to write a balanced equation. We've done that. Okay, we've got a balanced equation for the reaction being described. What is the second step in every single stoichiometry problem? Get something.
Get moles.
Get moles. We need to get moles. How are we going to get moles here? Well, what do we know about the krypton gas? We know its pressure. We know its volume. And we know its temperature. How am I going to get moles of krypton gas?
Using ideal gas law?
Ideal gas law, exactly. PV equals nRT. So yes, we're going to use PV equals nRT and solve for moles. We're going to get moles of krypton. And we have to do the same thing for the chlorine. Chlorine, we've got 1.5 atmospheres of chlorine. It's also 15 liters, also 623.15 Kelvin. And so we're going to solve and get moles. We always get moles. Okay, so if we're going to do this here, let's plug and shove really quickly. 0.5 times 15 divided by 623.15 divided by 0.08206 gives me, and you should check my math, 0.14, let's call it 67 moles of krypton gas. And let's see, 1.5 times 15 divided by 623.15 divided by 0.08206 is 0.4400. Okay, so there's our first step. All right, we figured out moles of krypton, moles of chlorine. Now the goal is to get the mass of the product, krypton tetrachloride. So what do I have to do next in this problem?
Find the limiting reactant.
This is a limiting reactant problem. If we're going to figure out the mass of the product, we have to decide which of these two reactants is the limiting reactant. Okay. So what's the limiting reactant here? Work it out right now. Everybody, all right, if you have 0.1467 moles of krypton mixed with 0.4400 moles of chlorine, and the ratio, the mole ratio is a 1 to 2 mole ratio. What's limiting and what's in excess? Work it out. Because by now you cannot hesitate on figuring out what the limiting reactant is. And it's never going to get easier than a 1 to 2 ratio, unless it's a 1 to 1 ratio. So you should be able to do the math in your head. So what's the limiting reactant here? We're looking for the limiting reactant.
The krypton gas?
It is. All right, limiting reactant is krypton. Chlorine is in excess. All right, we have actually 3 times the amount of chlorine. We only need double the amount of chlorine. Chlorine is way excess. And so now if we're going to figure out the mass of the product, we simply use the limiting reactant to do that, as we always do. All right, so we're going to take our 0.1467 moles of krypton, and it's a 1 to 1 ratio times 1 mole of krypton tetrachloride per 1 mole of krypton times, well, now we just need the molar mass of krypton tetrachloride. So let's take a look. Krypton, 83.8. Chlorine, 35.45. 83.8. So I get 225.6 here. Okay, so in the end, whoops, that's not supposed to be right there. So in the end, come on, here we go. I get, let's take this value, multiply it by 0.1467, and I get a final mass of, if I'm rounding, 33.1 grams of KrCl4 are going to be formed. Okay, so that's a classic stoichiometry problem. It's just a limiting reactant problem. It's a limiting reactant problem involving gases. That's all. Any questions about this one? Okay, looks like we're good here. So that was number 71. The next question on the list here is 81. Okay, everybody turn to number 81 while I get this problem erased. Okay. So number 81 is a question involving partial pressure. And in this problem, it says, determine the partial pressure of each gas shown in the figure below. It says, note that the relative numbers of each type of gas atom are depicted in the picture. Okay, so we've got a container, and I'm not going to draw it as precisely as the picture in the diagram. And let's see, we've got here, I'll use some colors here. I've got some reds, and I'm going to keep the dots the same.